Okay, so I showed in the last video, the video titled Two Tables, I showed how to solve a complex circuit using two tables. But for some of us, the two-table method just does not make sense. And so because of that, I wanted to show you another method where you can do it all in one table. So let's go ahead and add some values here. Let's say this is, I don't know, 30 volts. Let's make this resistor 1, let's make that 5 ohms. Let's make resistor 2 6 ohms, and resistor 3 3 ohms. Okay. Now for this circuit, again, I'm showing you a lot of ones where you'd have to squish parallel branches, but that's most commonly what we see. So in this one, you would smoosh or squish these two parallel branches, so you would wind up effectively with a series circuit. Okay, but if you don't want to redraw the circuit or you don't want to draw two tables, there's a way around that. So what I'm going to do is I'm going to say that for R2 plus 3, that's going to be in series with R1, and then let me just show you. So I'm going to draw my ones that are in series with one color. Okay, so R1 is in series, and then R2 plus 3 is also in series, and that's going to have the total row. Okay, R2 and R3 are really in parallel. Okay, so drawing it this way helps because you've got it all in one circuit. You don't have to mess with transferring information from one table to another table. But for some people, you know, the other way is better. Me personally, I like this way, but everybody's different. Okay, so if it's written in orange, that means it's the current going through resistor 1, and then we're looking at the network, what's coming back out, kind of 2 and 3. Okay, so if it's in orange, the way I've written it, that's going to be series rules, where current is constant and everything adds. If it's in purple, that's going to be parallel rules, where voltage is constant, resistance is weird, and current adds. Okay, so let's go ahead and put in our given information. We know our total voltage is going to be 30 volts. And we know resistor 1 has a resistance of 5 ohms. Resistor 2 has a resistance of 6 ohms. And resistor 3 has a resistance of 3 ohms. So again, just like the other way, the first thing we need to find is what goes in this box here. Then we can find our total resistance, which will lead to our total current. So again, we're going to do 1 over R2 plus 3 is equal to 1 over R2 plus 1 over R3. So in this case, be 1 over 6 plus 1 over 3. These fractions are so easy. So if you multiply this by 2 over 2, you get 1 over 6 plus 2 over 6, which is 3 over 6. And then you flip it, so it's 6 over 3, so the equivalent resistance is 2 ohms here. Oops, and I wrote it in the wrong color after I just lectured you about color. So 2 ohms, that should be series. Okay? Now, what we can do is we can say, okay, I know that 5 plus 2 is equal to 7 ohms, and I can use that to help me find my total current. So V is equal to I times R. We're solving for current. We need to divide both sides by R. So V over R will give me current. Okay? So 30 divided by 7 is 4.29. It's 4.2857. We're going to call it 4.29. And then we know because it's orange, it's in series, the current is constant, so every other orange row gets a current of 4.29 amps. Okay? Now, because we know that, we can calculate voltage, because voltage is equal to current times resistance. That's already arranged for you to solve for voltage. You just multiply current times resistance. So 4.29 times 5 gives you 21.45. 4.29 times 2 gives you 8.58. So we're going to be a little bit off here. So 21.45, this is how we check. Remember, if we add these two voltages up, they should equal 30. We're going to be a little bit off because of rounding, but it's not going to be a significant issue. Yeah, so if I add these two together, I get 30.03, which is close enough for our purposes anyway. So that enabled us to figure out the current through R1, the total voltage across R1. Okay? Now, for R2 and R3, we know that the voltage that runs through R2, the voltage drop across R2, rather, I should say, should be the same as the voltage drop across R3 because those two are in parallel. So when the charges get to this point, they'll have 8.58 volts of energy, and they'll use that going through R2 if they take that path, or they will use it all going through R3 if they take that path. Okay? So we're going to put 8.58 volts here and 8.58 volts for R3. And we're going to solve for current again, and that, remember, that's what we did down here where we divided the voltage by resistance. So voltage of 8.58 divided by our resistance of 6 gives us current of 1.43 amps in R2. And then 8.58 divided by a resistance of 3 gives us a current of 2.86 amps for R3. So I just want you to look at something really quickly. If you notice, the resistance of R2 is twice as much as the resistance of R3. And if you'll notice, R3 gets twice as much current as R2 does. That's because, remember, the charges are lazy. They don't want to go through a higher resistance component. Okay, so let's do our check again. If we've done this properly, when we add the current through R2 to the current through R3, it should give us our total current that we found. So 1.43 plus 2.86 gives us 4.29, which is exactly what we want. Okay, so then you could use this table to answer questions about, okay, I might cover up this row though, so that it's not as confusing. And I might say, all right, well, my total current is 4.29. I could tell you that the current through resistor 3 is 2.68 amps. I could tell you the voltage drop across resistor 1 is 21.45 volts. So again, it's just a matter of personal preference, whichever one you decide. If you're struggling with one way and haven't tried the other, go ahead and try the second way and see if it helps. Fine, I'm going to add it like I add everything else. If you have any questions, please ask. We're here to help you, but we're not mind readers. Hope you have a great day, and I hope you're having fun preparing for your test. Thanks.